Okay, so today we're going to cover statistical hypothesis testing, the Z-test. So make sure you've already taken the probability review quiz on Canvas under topic 9 before you listen to this lecture. I hope you prepare for it. Okay, so here's the scientific method. We've talked about this before. It all starts with generating questions. Maybe you review the literature, what's already been done, research. You might look around, you might be at a playground. You might notice that, little boys tend to use more physical aggression if bullying, and little girls use relational aggression. You might have oh, wow, why is that? And you might develop some hypotheses, formulate your predictions, and then design and implement your study, collect some data. And then you'll test your predictions with statistical analyses. And that's what we're going to focus on in this class. And this unit is when we really get down to what we're going to do to test predictions. Okay, so let's review some terminology. Population is the complete set of events, individuals, it's everybody. Sample is a subset of that population. Parameters refer to numerical values summarizing population data. So mu is population mean, sigma is population standard deviation. We've already seen that, right? Statistics summarize sample data. So we have mean or X bar. We have samples. We have S, sample standard deviation, R, correlation, and so forth. Sampling error occurs. So that's when random chance produces a sample statistic that is not equal to the population parameter it represents. This means the sample is not representative of the population. We use inferential statistics to decide if sample data represent a particular relationship in the population. The likelihood of obtaining that sample given a certain population. So we make hypotheses about populations and not samples. So when I ask you to write out the statistical hypotheses, just remember you're going to be using Greek letters because we're talking about population. So to repeat, inferential statistics are used to draw conclusions about populations based on samples. This is because populations are too big. We can't test everyone. Your textbook definition of hypothesis testing, a process by which decisions are made concerning the values of parameters, population parameters. We use statistics obtained from our sample to draw conclusions about population parameters. H sub 0 is how we denote the null hypothesis, which is always of no effect, no difference, or relationship. The null hypothesis will always have an equal sign in it. We denote the research or alternative hypothesis as H sub 1 or sometimes H sub A for alternative. This is what the researcher believes is the case. Here are our hypothesis testing steps. First, we state the null hypothesis and alternative hypothesis. We set the alpha level or decision criterion. We state our decision rule, collect the data, calculate our test statistic, T or Z or whatever, which corresponds to a p-value. We refer to our decision rule, which is usually reject the null hypothesis if p less than 0.05. And then we state our statistical conclusion, which is reject the null hypothesis or fail to reject the null hypothesis. And we describe the results in language anyone can understand. So the experimental hypothesis is what the researcher expects and hopes to find. So for example, we might think that people with greater cognitive flexibility will be happier. The corresponding statistical hypotheses, okay, are just the expected population parameters the sample data would represent if the predicted relationship does or does not hold. So corresponding to our experimental hypothesis is the alternative hypothesis. So H sub 1 or HA, there will be a positive correlation between cognitive flexibility and happiness. And we would write this out as Greek letter rho, this is a lowercase rho, greater than 0. Our null hypothesis is that there will not be a correlation between cognitive flexibility and happiness. It'll be, and technically, rho less than or equal to 0. Remember, there's always an equal sign in your null hypothesis. So how do we test them, right? What if we just, instead of having a directional hypothesis, if we don't think there's a positive correlation, we just say there's going to be a relationship between cognitive flexibility and happiness, right? This would just mean that the population parameter rho, which is the correlation of the population, is not equal to 0, because if it were no relationship, it'd be 0. And the null is that rho equal to 0. Now we've seen these data before, right? We run a correlation analysis, and we've already used Pearson's R, right? 0.458, right? We have not been referring to the p-value. Now, in SPSS, it's not going to say p, because what SPSS puts is it says significances. It says SIG, which stands for significance, okay? But it's the same thing, right? So we would write R, so that's Pearson correlation. Pearson's R equals to 0.458, p less than 0.001. The correlation between cognitive flexibility and happiness is statistically significant. This is all jargon, right? Plain English would be people who have greater cognitive flexibility also report being happier, right? This p less than 0.001, this means that the probability of getting a correlation of 0.458 if the null were true, the null is that the correlation in the population is 0, it's very, very unlikely, okay? So to rephrase, statistical significance refers to the probability of a given statistic if the null hypothesis were true. The probability of obtaining our data if in the population there were no relationship. The null hypothesis is always that there's no effect. That's what we want to disprove. So for example, again, cognitive flexibility, our alternative hypothesis is rho greater than 0. In other words, a positive correlation. The null is that rho less than or equal to 0. We can never prove that our hypothesis, our experimental hypothesis, is true. There is no such thing as truth in statistics. We just gather good evidence that the null is not true. We want to show that the null is very, very unlikely. So back to our example. R equals to 0.458, p less than 0.001. And the p less than 0.001 is the probability of this result, R equals 0.458, if the null hypothesis of R equals 0 were true. It is statistically significant. That's the term we use when p is less than whatever our criterion. In this case, it's less than 0.001. Our criterion was 0.05. Remember, we're talking about probabilities. There's still a very small chance that the null could be true because we could have just sampled extreme scores, right? So as researchers, we have to accept that there's a risk of us of falsely or incorrectly rejecting a true null hypothesis. And we specify the level of risk we're willing to accept before collecting data and running statistical tests. So alpha level, which is that criterion, the risk we're willing to accept, is usually 0.05. We denote this alpha, which is a Greek lowercase alpha, okay, equals 0.05. Our decision rule will be if p less than 0.05, then we reject the null hypothesis. In other words, if the probability of our findings given the null hypothesis of no effect is less than 0.005, we can reject the null. So let's talk about the formal terms. It's all about falsification. This is science, scientific logic. To support a claim, we must falsify the opposite claim. This is why it's so important to have testable hypotheses and have falsifiable claims, right? So we have to figure it out so that can be done. If we cannot test a hypothesis, if we can't falsify the null, then we can't do science. The null is the initial assumption of no effect. The alternative is the opposite of the null, that there is an effect, whatever we expect. The alpha level is also called the type 1 error rate. This is how unlikely a sample result has to be in order to establish reasonable doubt about the null hypothesis. So generally 0.05 or 5%. This is the level of risk of finding an effect when there really is not one that we're willing to accept. More terms. Reject the null. That's when the probability of our result is less than the value specified by alpha. Okay, this is what we want to do. Okay. When we reject the null, we have a pretty good degree of certainty that the null is false, but of course, there's no such thing as truth. We just think, right? We want to reject the null. The other thing that can happen is fail to reject the null hypothesis. This is when the probability of result is greater than or equal to the value specified by alpha. So greater than or equal to 0.05, we fail to reject the null. In other words, our sample result would not really be surprising if the null were true. This does not support the null. We never accept the null, okay? We are trying to falsify it. So we failed to find sufficient evidence to falsify it, but this can say nothing about the truth of the null. We don't want this, but sadly it happens, right? So let's pause this video now and we'll make the next one.